Hello, Mr. Ryan, are you alright?
Yeah.
Okay, that's it. No more.
Yeah.
Okay. Yeah, that's it. We talk about the graph equivalent for a few days now. We talk about Dijkstra. We talk about Freud, water. We talk about breadth search, depth search, and also one is missing, uniform cost search. These currently are 5 shortest path algorithm we know. Okay. Dijkstra, weighted. Yeah, we can use it on weighted. Freud water weighted as well. Breadth search unweighted. Depth search unweighted. Uniform cost search is a variant of Dijkstra which is weighted. Right? The time complexity, this one, O E plus V log V. Freud water OV cubic. Breadth search OV plus E. Depth search is the same, just differs the way that expand the nodes. Uniform cost search is the same as that. Okay. This is the time complexity. Okay, so when we talk about the complexity, for example, the breadth search, depth search, we usually like to represent it as a V plus E, vertex and edges. But sometimes we can also use this O, B, D. Okay, B, D. B to the power of D. B is the branching factor. So for example, a tree, right? A tree, we talk about the trees. A tree, branching factor here is 2, right? Because each node has 2 kids, branching factor 2. D is the depth. Okay? So you can imagine that in order to do this depth search or breadth search on this tree, binary tree, the time complexity is O to the power of D. Right? Because at each depth, if we increment the depth, number of nodes will be double. We also talk about the iterative deepening long time ago. Iterative deepening search. This is basically like a breadth search and depth search combined together. The problem with breadth search is that we need a space to store all the nodes in the same level. So the space complexity for this one, if we talk about this B and D, is O B to the power of D. The space complexity, or OV. Right? But for the depth search, we only need to store we need to store 1 node per level. So the space complexity is OD. The breadth search gives these optimal results on an unweighted graph. If we search, the first node it finds is the shortest to the source. The problem is that it uses too much space. The depth search, it uses less space, but it's not optimal. For example, like if the optimum node here is here, right? And the depth search finds another node here, and you return. It doesn't find this one. Right? It's not optimal, it's not complete. Iterative deepening search, on the other hand, is a combination of depth search and breadth search. So we have a limit. So we have a D. So at the beginning we set that D equals 1. Then we perform the depth search. But when the nodes are beyond this D, the depth D, we stop. And if we find it, great, that's the optimum, right? Because the D now is the minimum, right? It's the minimum. And then now, if we don't find it, we increment D to D equals 2. And then we perform a depth search with D of 2. DFS, actually, we perform a depth search with maximum depth equals 2. Sometimes we call it depth limit search. Okay? And if we found the node, that's the optimal node. But if not, we keep incrementing the D until we find it. 1. So the node we want to find is somewhere here, this node. Yeah? For the depth search, do this. Right? Do this. For the breadth search, do this. Yeah, we find it. This is the optimal. Well, for the depth limit search, iterative deepening. Okay, so we set the limit to 1 node. So we perform a depth search, and that's it. We increment the D, and we perform a depth search. That's it. We don't find any. And we increment the D, and we perform the depth search. And we still don't find it. And then we increment the D, we perform the depth search. Okay, and then we find it. So this way, we combine the depth search and breadth search. We are into this iterative deepening. We have talked about this iterative deepening a long time ago. Okay, so look, D equal at the beginning we set at 0. So while d is smaller than, look, we have defined this iterative deepening search with the graph, and we want to find the shortest path between S and E. So look at the iterative deepening search. Usually we use it on a weighted graph. Okay, while d is smaller than the maximum, so usually we want to give a maximum depth, right? So in a graph, the longest distance it can travel is the number of vertices, right? Yeah. The longest. So we can say n equals the length of G. If this G is adjacent metric, adjacent list, okay, adjacent list. Answer equals depth limit search. With this G, we want to find the S to the N, and with the depth, right? If answer is we found it, if we found it, then we return answer. Otherwise, we just increment the depth, right? And then return here will be return not found. Right? So look, this is iterative deepening. So we just a while loop to increment the depth, max depth. If we don't find it, we keep incrementing the d. This is the depth limit search. Depth limit search, DLS is basically DFS plus a max depth. Okay. So what's max depth is that if the depth goes beyond a d, then we stop. We don't continue. Okay. Look, this tree might be very deep, right? Okay. So if I'm saying d, the maximum d equals 3. Okay. Then if we perform a depth limit search, what happens? Look, what's the depth limit search? Like 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if we perform depth limit search on this graph, on this tree, and with the limit 3, so what's the order? What's the depth search order with the maximum level 3? 1, 2, 4. Should we go beyond?
No.
Because it reaches limit. Then we go back 3, 5, 6. That's what it means. Yeah. If we don't find it, we keep incrementing this. Depth limit search. Iterative deepening. Okay, that's great. Okay, we can implement the depth limit search. But first of all, let's implement depth search, and then we can change it to depth limit search. Define depth search. We want to find the S to the N, right? Okay. So if S equal E, then we return 0. We find it, right? If the star is the same as the destination, then we find it. Okay. Then, if not, then answer at the beginning we set it to infinity. For the next vertex in GS, and answer equals mean answer DFS VE, right? Need to plus 1 here. Yeah, need to plus 1 and return answer. So look, this depth search is not very suitable in finding the shortest path because it needs to explore all the paths, and that's very expensive. Okay, that's very expensive. But one thing we can improve is here. The problem here is what? The other thing that is that if we're using the graph, we need to remember the nodes that have been visited. Otherwise, look, if the 1 goes to 2, 2 goes to 1, and then we don't want it to go in forth and back, right? So we first of all we need to add a sim here, a hash map, and then we can say if S in sim, then okay, return infinity. If we have found this before, we return infinity. And if not, the first thing is to put this S into the vertex that we have seen. So S sim dot add S. Okay. And before, because we added, so before that we need to restore it. So sim dot erase or remove S. Okay. So this is the depth search. Okay, so now we want to change this to depth limit search. So we have to add another parameter called d. And then here as well, if d is smaller than 0, then we return infinity. Right? And then we just have to give this parameter d minus 1 here. Right? And that's the depth limit search. Simple as that. Okay. So the advantage of iterative deepening is that it's complete as breadth search. It allows us to find a solution the optimal solution if there's any. It also uses the same memory as the depth first search, right? Because look at the depth first search, we don't need to store the nodes of the same level, right? We don't need to maintain a queue. We just need to remember the path, right? This path, it uses the less space than storing the nodes of the same level, right? Okay, so tell me, what's the iterative deepening search?
It's like breakfast search and breakfast search.
It's a combination of depth first search and breadth first search, right? So iterative deepening is like we are performing the depth first search, right? But we are performing in an incremental order. Let's do a depth first search, and then let's stop. Let's not explore the nodes beyond the distant one. Okay? If we find it, we return this is the optimum, right? Okay, we don't find it, right? Like 1 meter, we don't find it in 1 meter. Okay, let's increment the max step to 2 meters, right? And let's perform a depth first search on this graph and a weighted graph with max distance too. If we find it, great, we return. We stop the iterative deepening search. If not, we increment the depth to 3, right? The time complexity for this one is actually quite tricky. So if we perform this on this tree, for example, right? So look, the last level, D, only explore once, right? So it's B to the power of D. The second to the last level explores twice. So it's 2 times B, D minus 1. The third to the last explores 3 times, right? So it's 3 plus B, D minus 2, etc. So but the most dominating is this one. So the time complexity is the same as the depth first search and breadth first search. Is also OB B to the power of D. Right? Okay. The space complexity is the same as depth search, which is D. OD. Okay. That's it for today. Bye bye.
Bye.
Bye bye.